So continuing on with one last example, we're going to do potassium sulfide plus nitric acid. And that will react to form hydrogen sulfide plus potassium nitrate. All right, so what is going to be, again, we've got two nitrates. Our table in row 2 says that nitrates are just always soluble, no exceptions. Sulfides, we can see down at the bottom, are generally insoluble except with group 1 elements, such as lithium, sodium, or potassium. So K2S will be soluble, nitric acid is soluble, potassium nitrate is soluble. H2S, on the other hand, hydrogen sulfide, is a gas. And so we can probably already see what our driving force is going to be in this case. But we'll keep going. So we'll write out the ionic equation. And we can identify our spectator ions because they're the same on both sides. Potassium as well as the nitrate. So finally we can write our net ionic equation. S2 minus plus 2H plus react to form hydrogen sulfide gas. And so what's our driving force in this reaction? Driving force is production of a gas. Now, back at the beginning of this chapter, I made a brief reference to acids and bases. And now we're going to introduce what those are. And this is going to be sort of our brief introduction to acids and bases. We're not going to get into any of the math that we need to do things like calculating strength of an acid or a base, but just give ourselves sort of a very brief overview that we need to get started in this area. And the first thing, most important thing, is we need to define them. And we've actually got 3 different definitions for acids and bases. We're going to start out with the oldest of the definitions, known as the Arrhenius definition. The Arrhenius definition says that an acid reacts with water to form H3O+. Whereas a base reacts with water to form hydroxide. Now, this definition's okay, but we don't use this definition all that often, and one of the reasons is it limits us to just water. So we go to another definition, which is known as the Bronsted-Lowry definition. And the Bronsted-Lowry definition says that an acid is an H plus, or we'll say a proton donor. So how is it that we can say that H plus is equivalent to a proton? Well, if you think about what a hydrogen atom is, a hydrogen atom has one proton, one electron. If we now have a cation of that, that means that hydrogen has given up its electron. So what's left? Just a proton. And then a base is referred to as an H plus or a proton acceptor. And this definition is definitely more thorough, more useful than the Arrhenius definition. But it turns out there are a few compounds out there that exhibit the behavior of acids or bases. Aluminum chloride is a good example. Aluminum chloride is recognized as an acid, but it can't be a Bronsted-Lowry acid. Why not? Well, aluminum chloride doesn't have any hydrogens. If it doesn't have any hydrogens, it can't donate any hydrogens. Additionally, and we haven't really started talking about reactions, and we won't for quite some time, but it's important to think about then when we will start learning about reactions. What really determines how reactions take place is what the electrons are doing. Acids and bases reacting are reactions, so it is largely based on the electrons. So maybe ultimately it makes the most sense for us to have a definition here that is based around the behavior of the electrons. And that brings us to the Lewis definition, which is the most thorough definition of acids and bases. We will very often still use the Bronsted-Lowry definition, but the Lewis definition is also important. The Lewis definition says that an acid is an electron pair acceptor and a base is an electron pair donor. All right, so just to look at how these types of reactions work, something like hydrochloric acid, HCl, will react with water. And does so by donating an H plus to form H3O plus, which we refer to as a hydronium ion. Plus Cl minus. HCl is something that we would refer to also as a monoprotic acid. What do we mean by monoprotic acid? It means that it has exactly one H plus to donate. And other acids that fall into this category are things like HI, hydroiodic acid, nitric acid, or acetic acid. Now, one interesting thing about acetic acid compared to the others, I think in the examples of HCl and nitric acid and HI, it may end up being pretty obvious that these only have one H plus to donate because there's only one hydrogen in each of those compounds. That being said, it doesn't mean that all hydrogens can be donated. If we look at acetic acid here, we can see that there's actually 4 hydrogens in this compound. But not all hydrogens within a compound are necessarily equal to each other. So it turns out that in acetic acid, you may be familiar with acetic acid. If you're working with vinegar, the smell you get out of a bottle of vinegar, you're smelling acetic acid. But that H that I've indicated there in red, that hydrogen, we would call that an acidic hydrogen, meaning that's an H that this compound is willing to donate. However, the other 3 hydrogens are not acidic. And so acetic acid is not willing to donate those hydrogens. So even though acetic acid has 4 hydrogens in it, it's still a monoprotic acid because it only has 1 hydrogen that it's actually willing to give up. Now we do have acids that will give up more than 1 proton. Diprotic is a compound with 2 acidic hydrogens. And that could be something like sulfuric acid. In the case of sulfuric acid, both of those hydrogens can be donated. We can even have a triprotic acid. Triprotic acid has 3 acidic hydrogens. Something like phosphoric acid. Now, just because it has multiple hydrogens that it can give up, so for example, phosphoric acid can give up 1 to form H2PO4 minus. It can give up a second one. And it can give up a third one to form phosphate. It doesn't mean it's equally easy to give up each of those hydrogens. In fact, in general, it gets harder for each subsequent proton donation. For bases, we can see a lot of the same type of activity. So something like sodium hydroxide, which is a solid, dissociates to Na plus hydroxide. And so for right now, we'll basically recognize hydroxides as some of our most common bases, whether it's sodium hydroxide, potassium hydroxide would function in the same way. But if we move over to group 2, we could have something like barium hydroxide, which actually has 2 hydroxides. Same thing with calcium. And we would refer to these compounds as dibasic because they have two hydroxide groups that can react. Now, when we talk about how strong or weak an acid or base is, right now we're just going to say that a strong acid or base is one that dissociates fully in water. Now, that's a little bit vague, or maybe a lot vague. And when you take Gen Chem 2, and you have the sort of revisiting of acids and bases, that's where we'll talk about how we can quantitate this. Because, for example, HCl and HI are both things that would qualify as strong acids. They will both fully dissociate in water. But later on, we're going to learn, again, a numerical scale for this. And at that point, we're going to see that HI is on the order of 1,000 times stronger than HCl. So they're both strong, but they're not equally strong. And so a neutralization reaction takes place when we have an acid and base that react with each other. And in general, when an acid and a base react, we form some type of salt and water. And we can see this whether we're talking about, a strong acid reacting with a strong base. So that could be something like nitric acid reacting with barium hydroxide. That forms barium nitrate. Plus water. So the barium nitrate is our salt. And then we get two water molecules. But we could also see this if we did a weak acid and a strong base, or a strong acid and a weak base. So weak acid, strong base, could be something like hydrofluoric acid plus sodium hydroxide reacts to form sodium fluoride and water. Or as we said, we could also do strong acid, weak base. Now in this case, we actually just form a salt, ammonium bromide. But we're always going to form some sort of salt from one of these reactions. The other thing that we will get at times from an acid-base reaction is gas formation. For example, if HCl reacts with sodium carbonate, again we get a salt, sodium chloride. but we also form H2CO3. Now, as it turns out, H2CO3 is not stable and will fall apart and form water plus carbon dioxide. So typically, if you have an acid-base reaction that takes place with a carbonate in one of your starting materials, you'll end up getting a gas to form from that reaction.